This video is going to be looking at how we do calculations involving solutions. So a lot of the time in chemistry, we're dealing with reagents or things, chemicals that have been dissolved in water. Every time we deal with acids, they are dissolved in water. Every time we deal with alkalis, they're dissolved in water, and often salt solutions, precipitation reactions, we start with solutions. So we may have to do some calculations involving things in solution, and we would have a measurement of their concentration. So what is concentration? We've done about it in the rates topic as well. So we've got just how many particles there are in a given volume. So if we compare these two images here, and the little red dots are the particles of acid or salt or whatever is dissolved, and then the blue behind it is water. The one on the left is obviously a lower concentration, the one on the right is a higher concentration. And we use these sorts of diagrams maybe when we're talking about rates of reaction, collisions. So we have dilute and concentrated, which is not the same as saying weak or strong. Those are different words which actually refer to the tendency of acids to kind of split up. So we don't really talk about that at GCSE. So we want to only use the words dilute and concentrated. But actually, most of the time, because we're looking at calculations, we actually want a value, some sort of number to measure concentration in. So the units of concentration, well, we're looking at how much stuff. So we're looking at amounts of particles per unit volume. That means that the units of concentration involve two other units. So like speed in physics, speed is a measurement of distance divided by time. So our units would have two units in them, meters per second, miles per hour, something like that. For concentration, we've got amount of particles. The more particles we have, the more concentrated something is. And we measure amount of particles in chemistry in moles. And then our unit volume in chemistry is usually the decimeter cubed. Now, if we have a smaller volume with more particles in it, that means they're more concentrated. So it's not moles times dm cubed, it's going to be moles per decimeter cubed, again, like meters per second. That means that I can actually work out the equation for concentration without really needing like a formula triangle or anything like that, because if I know that concentration is measured in moles per decimeter cubed, that gives me the calculation. Now, I might want to rearrange it into a triangle. What you'll notice is that moles, because it's on the top, on this left-hand equation here, is going to go on the top. And I do moles over dm cubed, not moles over volume. Because I want to remember that it's volume in decimeter cubed, because a lot of the time in chemistry, in the lab, we measure our amounts in centimeter cubed. We have to take that into account and convert, just like we do for gases. How do I know when to use this equation and not to use the 24 decimeter cube? I should be given 24 decimeter cube in the question. So if I'm not given 24, I don't use it. And also, I would normally be given something like moles per dm cubed, or told it's a solution. So I know it's about concentration, not about volume. Sometimes, every now and then, you will also get your concentration units in grams per decimeter cubed. We don't use that regularly, but you might have to convert between moles per dm cubed and grams per dm cubed. And we're going to do that as an example in this video, so don't worry. What about calculating concentration though? So if it's just a simple case of I've got some information about a substance, I know how much of it I've got, I know the formula, and I know the volume that it's been dissolved in, and my final answer needs to be in moles per dm cubed. Well, the first thing here, this would be probably at least a 2, if not a 3-mark question, because the first thing here is I've got 12 grams of sodium hydroxide, but there's nothing in grams on this unit here. I want my answer to be moles per dm cubed. So, first thing I'm going to do is work out number of moles in 12 grams of sodium hydroxide. I go to my periodic table, I can work out the RFM of sodium hydroxide, 23 for sodium, 16 for oxygen, 1 for hydrogen, so that equals 40 in total. So my number of moles from our previous calculations on mass in grams is going to be 12 grams divided by the mass of 1 mole, 40. And that's going to give me an answer of 0.3 moles of sodium hydroxide. But I'm not down to my final unit yet. I've got moles, but I haven't got moles per decimetre cubed. I haven't been given decimetre cubed in the question either. I've been given 250 centimetre cubed. So there are 1,000 centimetre cubed in every decimetre cubed. So if I want to convert 250 into decimetre cubed, I need to divide it by 1,000. And that will give me 0.25 decimetre cubed. Now I've got moles, got decimetre cubed. My answer needs to be moles divided by decimetre cubed. So I'm going to do 0.3 divided by 0.25, and that gives me an answer of 1.2. That is my final answer in moles per decimetre cubed, because that's what I did. I did moles divided by decimetre cubed. What about if I had to do it in grams per decimetre cubed? So usually they'll give you your information in moles per decimetre cubed, and they want it converting to grams per decimetre cubed, and it might only be 1 or 2 marks, fewer than the previous question. And the reason for that is, if for a moment you imagined that you were asked to calculate from miles per hour into kilometres per hour, and say I had, 20 miles per hour, and I wanted it in kilometres per hour. What I would do then is I use the fact that 1 mile equals 1.6 kilometres. I don't care about the hours because they're both per hour, so that bit cancels out. If I do 20 miles in an hour, I would do 20 times 1.6 kilometres per hour. So I don't need to actually really worry about the hour bit. What I mean by that is we don't need to worry about, let's get rid of all that physics, don't need to worry about the per dm cubed bit because it's the same. So all this calculation is I've got moles of something. How many grams does that equal? Because they're both dissolved in 1 decimetre cubed. So it's just a mass in grams question. The question is just saying how many grams are there in 0.05 moles of sulfuric acid. So sulfuric acid is H2SO4. I'd work out my RFN. 2 lots of 1 plus 32 plus 4 lots of 16. That would give me 98 as my RFM of sulfuric acid. So then mass in grams is going to be my moles times my RFM. So therefore mass divided by dm cubed is the same as moles per dm cubed times RFM, because that top bit will give me my mass. So my moles per dm cubed is 0.05, my RFM is 98. My final answer would be 4.9 grams per decimetre cubed. Right, the real time you're going to get a lot of solution questions. Titrations and the calculations involved in titrations. So there are 2 times you're going to use a titration. One is to make a salt, And in that case, all I want to know is the volume of the two substances that I need. So the equipment is the same, whether I'm using this to make a soluble salt or whether I'm using it to find the concentration of something that I don't know about. So what have you got? Always, you've got some solution that you're going to suck up using a pipette. This here piece of equipment is a volumetric pipette. It's going to have like a little line up here. It's only going to measure a fixed amount, might be 25, might be 10. So it's a really accurate piece of equipment. For carrying out a titration, you need accurate volumes. So I suck up the pipette. It's not showing the filler at the top. You would have a little bulb at the top to use to actually operate the pipette. And I would pop that into a conical flask. We use a conical flask so that if we swirl it around, it doesn't spill out the edges. So that's my first piece of accurate equipment. My second piece of accurate equipment is for my burette. So because one of them I'm going to decide I'm going to use 25 or 10 and I'm going to measure that out first. The other chemical, the point of a titration is I don't know how much, in this case alkali, sodium hydroxide, I don't know how much I need to add to neutralise my acid. And that is what the titration is trying to find out. So I would fill the burette, doesn't have to go all the way to the top, and we'll talk about that in a moment. There's a tap at the bottom, and so I can then, after I've added some indicator, we're using phenolphthalein in this one, but you also need to know colours of methyl orange, which is also used a lot in the titration. Then you're just going to add from the burette, having written down the initial reading at the top, not all of it, so you're going to add the sodium hydroxide until the indicator changes colour. Having done that, you then take your final reading, so you know exactly how much alkali you needed to add to just beautifully neutralise your acid. So, and it could be that the acid and the alkali are the other way round. There's no real rules there for what goes in the burette and what goes in the flask. If I were doing this to make a salt, I would then have my numbers written down. I would pour away this solution with the indicator in it, and I would do the experiment again without indicator. I would take my 25 of acid, and I would use the volume that I'd written down to add exactly the right amount of alkali. That's so that we get a perfect salt solution with no extra acid or alkali, so that when we boil the water and make our salt crystals, there's nothing else in there. But actually another main use of titration is if I don't know the concentration of either the acid or the alkali, I can use mole calculations and the volumes I take down to work it out. So let's look at the next few slides. I'm going to look at the kinds of questions you're going to get on calculations for titrations, and also on the readings and the sort of way that people often go wrong or just mess it up and lose marks. So here's the first bit of a question. Well, actually, it's part D. I don't know what the rest of it was. But it's asking us to read from a burette. Everybody looks at this and goes, that's easy. I can do that. That's so easy. First place you could go wrong is often the table is written so that the after value is before the before value in the table. The reason for that is because in the third box, I'm going to calculate the volume added by taking away the before from the after. So it makes more sense to put the bigger number at the top so that when you do your taking away, you can see what you're doing. So that's one mistake people can make, mixing these two boxes up and then losing a mark because of that. The next bit we're going to point out in this question is giving the readings to the nearest 0.05. So we'll explain that when we do the after reading. So we'll explain that as we go along. So before reading, next mistake, burettes read downwards. 2 is up the top there and 3 is down below. So we're going from 2, 2.5, 6, 7, 2.75 is where that line is. So that's going to go in the before box. 2.75. So that is to the nearest 0.05, no problems there. Having a look at the after burette, that is now exactly on one of the lines. So again, I'm reading down the burette, 23.6. And most students will leave it there and lose a mark. The reason they're losing a mark is because they're not recognising A, what the questions ask them to do, and B, what the accuracy of a burette is. So we've got these lines in a burette, and we could definitely see when the water is on a line. But we could also see if the water was either above or below halfway. So when they say to the nearest 0.05, they mean it is possible to tell whether it is 23.55, 23.6 or 23.65. So I'm not just saying I know whether it's 23.6 or 23.7. I'm being more accurate than that. So if it is dead on one of the lines, the likelihood is you will need to write a 0 after it so that both these readings are now to the same number of decimal places, same level of accuracy. And then the final bit is just for calculating the difference, the volume added. Take one from the other and we get 20.85. Again, weirdly, quite a lot of students choose to do this calculation without a calculator and thus get it wrong because it's very easy to get things wrong by trying to rush. So there's no point rushing this. This is 3 marks. You've got 3 minutes to do it. Often then, we would move on and they'll give you different numbers. They give you different numbers because they don't want you always trying to carry on errors all the way through the question. I also know it's different numbers because we've now got part E instead of part D, whereas here I know that this part I and part II are related to each other. So this is quite a nice question because they've asked you to tick which results are concordant. And a lot of people would then go, I don't know how to do this because I don't know what concordant means without reading the bit above. So normally with a titration, I would do several experiments so that I could see which ones are the best experiments. And it tells you what the best experiment is. You're not expected to know that off by heart. The experiment values have to be within 0.2. So it's volume of acid added. It might be that there be more of a table, so it might give you all of the answers. So like that answer that you just did, it might have the start volume, the end volume, a big fat table, but this bit is the result, the volume added. So that's the bit we're comparing. First two values, 22.9 and 22.6. No, they are 0.3 out from each other. I'm not going to completely discount 22.9 because there might be another one close to it. So let's look at the next value, 22.6 and 22.45. Well, they are between 0.15 of each other. So they are concordant with each other. And then 22.55 is within 0.1 of the one on the left and 0.05 of the other one. So they are concordant. So there are 3. Sometimes there are 2. There's never only going to be 1 because a result cannot agree with itself. But there's usually going to be 2 or 3. So there's a mark for doing that. The next bit is simply calculating an average. If I add up those 3 numbers, I get 67.6. I divide it by 3 and I get 22.53 recurring. I'm going to leave it as 22.53. I'm not going to put the dot above it because my answer is not so accurate that I could have an infinite number of decimal places. Now we're on part C, so we've now got a new set of numbers. We're ignoring our last averages and everything else. We've got 3 numbers given to us and we're going to use them all the way through this question. So we're not necessarily going to need all of them in the first bit. So we've got all of these bits of information. You always get 3 bits in a titration concentration question. You will get the volume of something, you'll get the concentration of one substance, and you'll get a volume of another. And that's because we know the concentration of one substance. In this case, we know the concentration of the acid. We know the volume of the acid because we used a pipette, and I know we used a pipette because that's an exact number, 25.0. And then we'll know the other solution's volume because we would have added it using a burette, and therefore I've got two volumes, one concentration. I'm going to go via moles. Moles equals concentration times volume. That's a rearrangement of what we did before. To get from moles of this to moles of this, I can therefore work out concentration of my unknown. But it's going to step it out for you. So you've just got to keep your cool and work out what you need to know. So it says amount in moles of H2SO4, and it's actually given you a volume and a concentration. So I know it's 0.107 moles in every decimetre cubed. I also know that I have 25 centimetre cubed. Now these units are not yet compatible, so I'm going to need to turn my centimetre cubed into decimetre cubed. 0.025 decimetre cubed. Then what I do, well, if I've got moles per decimetre cubed, if I times it by decimetre cubed, they will cancel out and I will get moles. So if you would prefer it in that triangle we used earlier, moles is on the top, concentration, decimetre cubed on the bottom, and I'm trying to find moles, so I times them together. So I've got 0.107 moles times by 0.025 decimetre cubed, and that is going to give me 0.02675 moles, which is my answer there. So I changed my volume to decimetre cubed, and then I times it by moles per decimetre cubed to get moles. Having got that answer, that was part I. So I'm now going to use the same number in part II. I've not moved on to part D or E or F. This is still part of the same question. It's still part of the same titration. So this is where people could get confused. It says calculate the amount in moles of lithium hydroxide in 22.85 of lithium hydroxide solution. Only one mark. And I actually don't need to use this value yet. This is just the value that came out of the burette. What I use now is if I'm going from one substance in moles to another substance in moles, then I need to look at the balanced equation up here. So any time where I've just done something about one chemical and I now need to infer something about the other chemical, I need to use the balanced equation at the top of the page. So the balanced equation tells me 2 moles of lithium hydroxide react with 1 mole of sulfuric acid, because there's a 2 in front of my LiOH. There is no 2, so it must just be 1 lot of H2SO4. So if I've got 0.02675 moles of H2SO4, I would need to times that number by 2 to get my moles of the other substance. So I'm going to times it by 2, and that means my lithium hydroxide is 0.00535 moles of lithium hydroxide. That's what I'm going to put in that box there. So I've got as far as I did moles of acid using my volume times concentration, or decimetre cubed times concentration. And in this bit I used the equation because I went from acid to something else, so I had to use the equation to see how they related. Then I've got, again, a third part of the same question. So we're always going to use the last number in the next part of the calculation. 0.00535 is going to be important in this. That's my moles. I now want moles per decimetre cubed. And I haven't used this number up here, 22.85. That is in centimetre cubed. So whenever we get that, 22.85 needs to be turned into decimetre cubed, 0.02285. That's my decimetre cubed. I want concentration, so I want moles per decimetre cubed. I did moles in the last question, 0.00535. I did decimetre cubed just now, 0.0285, and I get my final answer as 0.234 moles per decimetre cubed. So tips for doing this. Tick off the numbers as you're using it. Make sure you are moving things from one part of the question to the next. If it suddenly changes and instead of saying part 3, it says D, you are now looking for new numbers, new information. If you haven't ticked off this volume, what can happen is you divide by the same volume again, so you're using the same volume twice. You should have used everything by the end of this question. The balanced equation, you should have used the concentration, and you should have used both of the volumes, and that's always how you get it. So what you would have is, somewhere in the question, you would have chemical X, chemical Y. And for one of, if we call X your unknown, you would have a volume for chemical X. You would also have a volume for chemical Y. So you must have 2 volumes in a calculation usually for titrations. And then you would have a concentration for one of them, such as Y. If you have volume and concentration, you can times them to get moles of Y. You would then go from moles using the equation, the balanced chemical equation, to get moles of X. You would then take your moles over your volume of X to get concentration. You'd have to do that in separate steps though, because normally it will do them in separate steps in the question.